So again, hope you guys are enjoying change your pace, I guess. But we're going to be virtual anyways, whether we had a NTI day or not. So really no different besides the fact that I'm at home and not in my classroom. It's really the only difference. I would rather do this NTI than be in school until at the end of May or June. So might as well. And plus, I had a schedule for the week, and so we had a true snow day. It would mess up the schedule. So I'd rather do this. I know that everybody needs a break every now and then. Hopefully, you took a break over the weekend, and hopefully, you'll take a break during lunch and this afternoon, especially if you have little brothers, little sisters. You know, be a good brother, be a good sister. Go outside and have fun with them for 15 minutes. Have a snowball fight with them. Don't eat the yellow snow. Okay, be careful of that. Right. I have two dogs, so my kid loved eating the snow, and I'm like, be careful, careful what you eat. All right. So real quick, let me share my screen, and we will talk about the weekly schedule, and then we'll start the notes for today. So if you want to go ahead and grab the notes, we are kind of starting a new topic. It's fairly similar, but it's going to tie in with what we did last couple of weeks. So. All right, so the weekly schedule, you'll notice right off the bat that today we have two activities that we're going to do. And that is kind of because the schedule got messed up because of case testing, but we'll talk about that in a minute. So again, make sure you do your check-in. The check-in is really quick and easy. And it's a way for me to make sure you guys come here and you guys get your notes and you guys get your stuff. So please do your check-in. There's a lot of kids that are not doing them. It's also a way I take attendance. So if I mark you absent, and then you come to me and you say, I was here that day. I look at your daily check-in. Did you check in, and were you really here? So if there's no evidence you were here and I marked you absent, well then you're gonna stay marked absent. So please make sure you do your weekly check-in, your daily check-in. Again, there are notes here that we're going to take. The link is right there, but you can click on either one of those to get your notes. And then today we're going to do a little activity. Okay. Wednesday, first thing you'll notice is that especially with the sophomores and freshmen, you guys are going to be doing your case testing Wednesday. I don't know exactly what the schedule is going to look like, especially after test, but you should have a lot of downtime on Wednesday, and therefore you should be able to just get some work done, whatever it is. You are probably not going to get your activities done today, A and B. We have a few notes and a few things we're going to talk about, but you will have 10-15 minutes to work on today. You will have that extra 30 minutes that you're with me before lunch. You will have home time at home for homework. You should have a little bit of time sometime tomorrow and Wednesday to get the activities finished. Note that on Tuesday, we are going to start a pretty intensive ACT lesson. It's a Kaplan lesson. I know that some of you are dual credit. I will exempt you like I normally do from Tuesday, Thursday work. However, even dual credit kids, you probably want to start checking out these ACT lessons. Okay, they are meant to help you do better on the ACT, and we are going to focus on the science part, obviously, for the next 4 or 5 weeks as the ACT is approaching. So again, sophomores, your ACT is March 2nd. So on Tuesday, Thursday, we're going to kind of be doing a little bit of a workshop. They are interactive lessons. There's really not going to be a lot that you can do right now working ahead, because I'm going to be like, hey, okay, it's time to do this. Let's do this. Time to do that. Let's do that. So it's going to kind of be an interactive lesson on Tuesdays and Thursdays for the next 4 or 5 weeks, practicing ACT skills. Okay. And then Friday, we'll do some more notes. Activity C, there is no quiz this Friday. Okay. The quiz will be next Friday. All right, so if you click on the note, you'll get this this worksheet or this set of notes here. Again, if you want to make your own copy, I encourage you to just click on the file, make a copy, and you can make your own. As always, I also encourage you to have paper or pencil and writing down stuff that is important and organizing these notes a little bit more. Then, of course, have conversations, ask questions about this stuff. One of the things I miss about being in a classroom is just talking about random things and you guys asking random questions about the content, and that are good, and we can have talks about those things. So if things pop up in your brain, you're like, oh, that's interesting. Let's talk about that. Ask questions, just type in a chat box. If you're too worried about, if you're too nervous or shy, put it in a private chat and let's talk about it. Okay. All right. So cases, English and math testing. I don't think there's any social studies, just English and math, I think. So you'll do like English in the morning. Well, you'll do them all before noon, but you'll do English first and then math or whatever it is. So it's the district content test. All right. So we're just going to kind of run through this real quick, but this part of the unit is focusing on stars. So we talked about the Big Bang, which is the formation of the universe. And then now we're going to be talking about the formation of additional elements that were part of our life. And so remember, we started with the Big Bang, and then stars come into play. And then stars are what kind of form everything else in the universe. So again, we're going to do some slides today. No lesson on Wednesday, some more stuff on Friday. Then next week, we will have a quiz on Friday over both week content. And I'll update the schedule as we get closer to that. All right, so stars. We're going to talk about the life cycle and types of stars and what they do. So stars are basically supermassive celestial bodies, with celestial meaning just being in outer space, that are mostly made of hydrogen and helium. And mostly hydrogen, though. And so they're basically just big, giant balls of hydrogen out there. Okay, and then when they all get together, things happen. So again, quick question: where did the universe get the hydrogen and helium to make the stars? Well, they got that from the Big Bang. Remember, we talked about the Big Bang made the building blocks. So the Big Bang itself did not actually make the stars. Okay, the Big Bang made the building blocks, made the matter to be proton, neutron, electron. Then years later, those proton, neutron, electron make hydrogen and helium. And then years later, the stars all get together when all the hydrogen bundled together. Okay, and they all bundle together due to gravity. So gravity is collecting or condensing, as we call it. Okay, it condenses the hydrogen and helium together to form stars. And if you remember, based on the timeline, this took a really long time after the Big Bang to form even the first stars. Okay, because again, that's a lot of hydrogen you have to gather together in order to make a star. Okay, and so correct me on my timeline. Was it 200 million years after the Big Bang? Something like that. Yeah. All right. So star, again, big ball of hydrogen, and that hydrogen came shortly after the Big Bang. Okay. All right. So why are stars so bright? Well, stars are massive. That's the first reason why. Okay, and because of their mass, they have a lot of gravity. Okay, and the gravity is causing. So gravity brings matter to the center of mass. Okay, and so in the center of mass, all that hydrogen is being forced together, and those hydrogen atoms can fuse together, what's called nuclear fusion. Okay, and so it starts to fuse hydrogen atoms together, and basically they are a supermassive nuclear furnace. They're basically fusing atoms together. So again, fusion is a process of taking two smaller atoms, whatever they are, combining them together to make a larger, different atom. And remember, protons do not want to be together because they are all positively charged. So in order to fuse atoms together, you need a massive amount of energy. You need the energy of stars. Okay? So in the process, this creates enormous amounts of energy and all forms of energy. Remember, we talked about electromagnetic energy. All forms of energy are coming from the stars, but definitely heat, light, even sound. So let me change my sharing my screen here. Make sure I got sound on. Turn my sound on. And so yes, our sun is making sounds.
You actually hear.
So this is the movement of that plasma of those gases, and they do create sound. The sun does hum. Luckily for us, we don't hear it. That would be super annoying, hearing the sound of the sun. Sound did not travel through space, in a vacuum of space, and it would also dissipate probably before it got to us, even if it did travel through space. So luckily, we don't hear the sun itself. But we can send out satellites and things around the sun and collect that data of what's happening to the waves, sound waves on the surface and what sound they're making. And so, yeah, the sun releases all, or any star releases all different types of energy. Okay. All right, so what we're going to focus on for this class is kind of the forces of a star and what's going on as a star is going through its everyday life and stuff. A star, again, has a lot of gravity that's got to fight. Okay, there's a lot of mass, so it's got to fight the gravity. So as it fuses hydrogen into helium, another element, this releases energy and it causes the star to expand. Yeah, that's really easy. You can even do it on your phone. I don't know what it's called, but it's called like a sound graph or sound wave app or something like that. But yeah, you've seen those before, like when people, little waves when you say stuff, and like a really common present for like a boyfriend girlfriend to say like "I love you" in a sound wave, and like. But yeah, you can definitely see sound waves, and you can record them with instruments. All right, so as the star releases energy, that is going to expand the star outward, and it's going to fight gravity, right? So gravity is going to pull the star inward. The energy is going to go outward, and you end up with a perfect sphere for a star, okay? And that outward pressure is called thermal expansion due to the energy, the heat energy, and it's going to push out in every direction. So in the core is where the nuclear reactions are taking place. Then that energy goes outward, okay, in all directions. Gravity, again, is forcing it back in. At a normal life of a star, you will have a balance between the gravity and the thermal expansion, and that is the size of the star. Okay. However, as the star runs out of energy in a nuclear fusion, in order to combat the gravity, the stars are going to expand and get bigger so that the gravity doesn't collapse them. At that point, you have an unbalance in energy and gravity. It's not at equilibrium anymore. And then two things can happen. Either the gravity will win the battle and take that star and condense it back down to a dwarf star. If gravity wins the battle, the star is pretty much done. It's just going to be a dwarf star and nothing really much is going to happen. It could continue to win and turn it into a black hole, which we'll talk about that later. The other option is that gravity doesn't win, the thermal expansion wins, and the star could expand and dissipate its matter or even explode in a supernova. Okay, so as the star runs out of energy, that expansion is going to cause two things to happen: either gravity wins or gravity loses, and then the star is going to change. Okay, it's going to change in some way. Okay, we'll talk more about that at Friday. Okay. Types of stars. There are lots of different types. They're mainly classified by mass, the size of the star. However, there are many different characteristics such as brightness, size, radius, color, temperature, the elements they make, the age, lots of different types of classification for stars. Most of the characteristics of stars will follow a pattern with each other, and I'm going to ask you guys to find one here in a second. So, for example, hotter stars tend to be brighter, and we'll take a look at that. Okay. When we classify stars, scientists compare other stars to our sun. They probably should have picked a different star because our sun is actually not that common, but our sun next to us, that's what we did. So they set the sun at a value of 1, and then they compare all the other stars to it. So for example, if there's a star that is twice as heavy, they'll say it has a mass bigger than 1. If a star is smaller than our sun, it will be a mass smaller than 1. If it is brighter than our star, it will be 2, 3, 5, 100 million. If it's dimmer than our star, it'll be 0.9, 0.8, 0.1, whatever it is, it'll be smaller than 1. So scientists compare all the other stars out there, and especially in our galaxy, to our sun itself. Again, probably should have picked a different one. So here are a bunch of stars, and in the chat box, I'm going to ask you guys a question here. What other patterns do you see? Okay. So, for example, we did this one here. We said the hotter the stars, the temperature, they tend to be brighter. So let's check that out real quick. So luminosity. So if I start with 20, this one is hotter. at 40,000, it is also brighter, right? So if it's hotter, it's brighter. So in the chat box, real quick, do another, write me another trend and use words like that. As this goes up, this goes up. As this goes down, this goes up. Okay, write me a quick sentence, take about 1 minute, and find me another pattern for stars. And again, I would practice this because you might see this again. Wink, wink, hint, hint. Yeah, so see what you guys got. The smaller the star. It's not necessarily the older it is, but it can last longer. Like it can get older. As mass goes down, temperature goes down. As mass goes higher, the lifetime decrease, or the temperature. Okay, good, good. We got 3 different ones there so far. Wait, other people, take about 30 more seconds. As mass lowers, yep, good. As radius increases, well, yep, that makes sense. As luminosity goes down, lifetime increases. Okay, cool, good. You got a lot of them. As mass decreases, so yep, that works too. Yep, awesome. All right, let's go back to those notes real quick. One that's really interesting, and I think some of you guys said it, is what happened with the temperature and the lifetime. So check out 40,000 Kelvin star. That's a pretty hot star. It has a lifetime of 10 million years. If the star is cooler in temperature, it can last longer. It has a longer lifetime, and that should make sense. Okay, it's 40,000 Kelvin because it's burning a lot of energy. It's using a ton of energy. It's really, really hot. Well, it's going to die faster. Okay, it's like driving a car. If you drive a car really, really fast, you're going to run out of gas sooner, right? You're going to run out of gas. So the same thing with this. Those stars are really hot. They're burning a lot of energy. They're going to die quicker. Okay? So we have these main sequence stars. Main sequence stars are just regular life stars. So they're just doing their thing. Okay. Then we have these things down here. These stars are running out of energy down here. And then, of course, the white dwarf star, it's basically done at that point. If it turned into a dwarf star, the gravity won and it's kind of finished at that point. So a question is mass decreases, so the temperature, mass, temperature. Yep, good one on that. All right, so real quick, we'll talk more about our star in just a second. Can you tell what type of star our sun is? So again, in the chat box, what type of star is our sun? It's on there. You can find it. Let's see if you guys can find our sun. What type of star is it? Caleb, are you thinking giant because it starts with the letter G? But it's actually not a giant star. It's actually pretty small. It's actually a pretty small star. All right. It is a G star. How do you guys know it's a G star? Yeah, you guys see. Good job, Anna Cameron. You guys see that on there on that paper there? So like again, all these values are set to 1, and then everything else is compared to our sun. So F is bigger than our sun. K is smaller than our sun. Okay, and so the sun is a standard, what we call it, and then bigger and smaller. Our sun is actually kind of a small star. Some people will call it a yellow dwarf star. It's not a dwarf star, but it's a small star. So, but it is a yellowy star. It's a yellow main sequence star. on there. And again, it's not a super common star, 3.5%. Most stars are red dwarf stars, really small red stars. But again, white dwarfs are pretty much the end of the life for a star. So giants, our star will eventually turn into a giant star when it runs out of energy. So again, this is a normal life, and eventually one of these will happen after this. Okay. All right. So, the cool fact about our star, again, in our solar system, our sun is about 99.8% of all the mass of the solar system. Jupiter and Saturn are pretty big too, but again, most of the mass is coming from our star. If Jupiter and Saturn were as big as our star, they would be bright and hot, just like our star is, but they're not even close to the size. Well, that's what they used to be, but then they will turn into a giant. So our star will turn in, because it is a G, it will turn into a red giant later. That is a good observation though. Okay. Over 1 million Earths could fit inside the sun, which is actually quite a bit. It is almost a perfect sphere because of that balance between gravity and energy. The sun is moving. It's moving about 200 kilometers per second. The whole solar system is moving. The whole galaxy is moving. So yes, the sun, it does move. Looking at the sun even for 1 second can cause permanent eye damage. Yes, especially when you have like a solar eclipse, people want to look at it. You can look at the sun during a perfectly total eclipse, but you have to be in a perfect total eclipse. That's the only time you can actually look at it with your bare eyes. So if you're in a partial solar eclipse, don't look at the sun. It could still damage your eyes. You can use certain glasses and telescopes to look at the sun. Just make sure they're the right one. Don't even your regular sunglasses. Don't look at the sun with those. But you can. There are certain solar glasses that you can wear and actually look at it. So, all right. So our sun. Our sun is the star at the center of our solar system. It is a near perfect sphere. It's hot plasma, so it's that matter. It's not a liquid. It's not a solid. It's not really a gas. It's a plasma, which is superheated gas. And it's heated to incandescent level, which is the light you see in the heat, by nuclear fusion that's happening in its cores. So again, it's radiating the energy outward, and mainly in the form of light and heat that we see, but all forms of energy, X-rays, gamma rays, radio waves, microwaves, all those energies are being, spewed out by the sun. And it's by far the most important source of energy for life on Earth. And again, our sun is a G-type main sequence star. To be really, really specific, it is called a G2V star, which is just more specific about the G stars. So even the G stars themselves can get more narrow, and that's the technical classification. Our sun star does not have a scientific name. It doesn't really have a number abbreviation or anything else like that. It's just called the sun. Latin for it was Sol, S-O-L. That's a Latin word for sun, which is where we get the idea of solar system. That's Sol means sun. Our sun began about 4.6 billion years ago from the gravitational collapse of matter within a region of a large planetary nebula cloud. So this picture here, obviously, is a artistic picture, but this is an example of a nebula cloud, okay, a planetary nebula cloud. Sorry, I should call it that. So this cloud came from a previous star that blew up and spit all this stuff outward, okay? And then our sun is in the center where gravity brought all that stuff, all that hydrogen back to the center, and that creates, because again, that's what gravity does. Gravity pulls the matter to the center. And that's the center, and that is where our star came from. So a previous star blew up and made that. All the other stuff is flattened into the disk because of movement against gravity. And all that other dust turned into the planets, turned into Earth and the moon and asteroids and comets and meteors and all that stuff. They're all remnants of the stars that blew up before that. So there is evidence that our sun is a third generation star, meaning that there were two previous stars before our star, and those stars probably had their own solar system. And then again, they expanded when they ran out of energy, and they blew up and made a new solar system, a new star. And then that star blew up. That star blew up and made a new one. And the reason we know that, good, oh, I didn't even see your question. The reason we know that is based on the elements that are in our solar system. So we have 90 naturally occurring elements in our solar system. Well, stars are only hydrogen and helium. And so the first stars are only going to make certain elements. And then they're going to blow up, make new stars, and then those stars are going to make more elements. And then they're going to blow up. Okay. And so based on how many elements that we have in our solar system, kind of tells us how many stars did it take to make those elements. And we'll talk a little bit more about that next week, because next week is about the formation of elements. But stars are fusing together hydrogen to make bigger elements, and it takes a lot of energy to make 90 of them. Okay? Our sun itself is only making 6 elements right now, all the way up to carbon. So there is did the star left out before? Yeah, probably because of those elements that we have. It probably did have other stuff. Then of course, that star, when it blew up, took out the solar system. It took out its solar system, and then that solar system is now making. So, like for example, like when that other star blew up, it left big chunks of rocks and garbage out there, and all that stuff got together to make planets. Okay, on there. So it had a core, and it spit all those things out, especially iron and things like that. So the sun right now, currently in its core, is fusing about 6 million tons of hydrogen and helium every second, which is a ton. It's converting about 4 million tons of matter into energy every second as a result. But what's really cool, so that's happening at the core, it's fusing the hydrogen together because of gravity. And that's where gravity is massive at the core. Okay. But that energy takes at least 10,000 years to escape the gravity of that star, of our sun. So that energy that's hitting you when you go outside, it took 10,000 years just to get out of the sun. And then it travels across the outer space to Earth. And then it hits you. Okay. So that energy that's hitting you, the light, the heat, all that, took a really long time to get out of that gravitational field. Okay. But it's making enough to where we're getting a constant source of energy. Okay. And again, that fusion in the core is the source of heat and light and sound and all the energy that's escaping. Okay. There's a lot of gravity. All right, so again, right now, our sun is at equilibrium with a size called hydrostatic. So again, the fusion energy is pushing out, gravity pushing in, makes it a perfect sphere. Okay. But eventually, it's going to run out of energy, and the star is going to expand to fight the gravity. Okay, and our star will eventually turn into a red giant. Like I think it was Caleb that said that. Our star will eventually turn into a red giant. When it turns into a red giant, it's going to eat up Mercury. It's going to eat up Venus. Scientists don't think it will eat up Earth, but it will come close enough to Earth to basically make it uninhabitable. It'll be too hot to be that close to Earth. But then eventually, after it turns into a red giant, again, either the energy will win and it will dissipate its matter, it will blow up, or gravity will win and turn it into a dwarf star. We don't know exactly what will happen, okay? But again, scientists don't think that is going to happen for about at least another 5 billion years with a B. So our star is still kind of relatively young. We don't have to worry about that right now. But eventually it will. It will expand to fight the gravity. Then it will either beat gravity or gravity will beat the expansion, turn it into a dwarf star. I think that's about it. Okay. That is possible. Yep. And yeah, that is possible as well. Like if it did not take in Earth and then it collapsed back at the dwarf star and maybe even a black hole, turned into a black hole, then it could absorb more material. Again, it's just gravity doing its thing. All right, there are additional resources about stars in general, about our sun. There's a couple. I like this video here called "Largest Star in the Universe." It's comparing our sun to the largest star. It's kind of long, but it shows you how small our star really is. Our star is pretty small. And then there's a little simulation from NASA here. Lots of information. So again, if you have more questions or if you don't understand anything, highly encourage you to check out the additional resources. All right, today we're going to do about 10 minutes, 10, 12 minutes working together on activity. So the activity is called Star Cycle Activity ABC, but today we're going to do A and B. You have all the resources to go ahead and work on C if you want, but you don't. But we'll do C on Friday. But today we're going to work on A and B. You're probably not going to finish today. That's okay. I kind of planned on that. But I would like for you guys to actually work together to do part B together. Part A is going to ask you to watch a video about star spectrum and star types. And you can do that on your own time, just watching it's a short little video and you're answering a couple questions. But together, I'd like for you guys to talk about part B, what's going on with our sun, okay? And I'd like for you guys to have a discussion and talk about it, help each other out with this. But again, don't copy off each other. But, discuss, where does our sun, don't ask you basically 3 questions. Where does our sun come from? What's it doing today? And what will happen in the future with our sun? Okay, so discuss that, talk about it, look at the notes, all that kind of good stuff. All right, so we're gonna go into breakout groups. I'm gonna stop the recording because it doesn't record the breakout groups. And again, I highly encourage you guys to talk and be friends and talk to each other. So work on part B as in boy together. Again, that's on Canvas if you need to find it on a weekly schedule. To work on part B together, you can do part A on your own time. All right. So we got about 12 minutes to work together, and then we're here for another 30 minutes if you guys want to keep working. All right, you're going to start disappearing here in a second. Did Kara ever show up? Nope, I don't see her. All right.